YouTube. I took my background off. I noticed that it was a little bit distracting. Wow, this is shaky. Okay, desk is a little unstable in its new spot. Okay, so no notes. Are there any questions actually before we get going? Questions about anything? Mm-hmm. All right, so today we're talking about Thanos' favorite subject, equilibrium. I guess balance was Thanos' deal, but dynamic equilibrium. When we talk about chemicals, we talk about reactions. Very often talk about them in a single direction. So everything that we've looked up until now, except for water, like so yesterday we talked about acids and bases. We talked about how water can self-ionize and how you get in neutral water 10 to the minus 7 molar hydrogen and 10 to the minus 7 molar hydroxide. And that occurs because there's an equilibrium. So the water is constantly switching from maybe your hydroxide to your water to your hydronium and back again. But the rate at which it does so balances out at, 10 to the minus 7 for each of those in molarity. Um, the rest of the reactions we have mostly talked about is going in a single direction, but that's not the case. Most of the time, there's a backwards reaction as well. So we have our reactants combining to form new products, but then those products, depending on how stable they are, can break apart again and give us our reactants back. And so it's this flow in either direction that gives us an equilibrium and can tell us something about how far exactly that reaction will go. So if we look at, or if we think about a freeway is a pretty good example of this, right? You have cars going in one direction, you have cars going in the other direction. And if you imagine two big parking lots, just zoom in here. So let's say you've got a parking lot here, and we have a parking lot over here. And for whatever reason, we have this freeway. We have cars going this way, and we have cars going that way. And then we have a lot. Just going to draw some expertly drawn. The only way this could be better is if it was done in MS Paint. So we've got cars on either side, and they're turning around and going back the other way. So if these rates are the same, if we have the same flow of cars going this way as we do coming back the other way, then the number of cars in each parking lot will remain the same. But if there's an accident on this freeway, and suddenly we can't get cars going that way, or we can only get a few number of cars, maybe we've blocked off all but one lane, then we're going to get cars accumulating in this right parking lot. And so that's what we're talking about today, is what happens when, or what does an understanding of equilibrium let us do? What does this unlock in sort of our chemistry toolkit that we've been building up? And so, yeah, the overlay here too shows that this N2O4 going back and forth between N2O4 and NO2. And so that's kind of our freeway here in our parking lots. The rate of a chemical change is what determines the equilibrium. So a chemical system is at equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. So at some point, and we'll see why this is, the rate in one direction will slow down and the rate in the other direction will speed up until they're the same. So the rate of a chemical reaction is a measure of how fast the reaction proceeds. So how fast are we turning our reactants into products? How fast are our cars driving from one parking lot to another? And the amount of reactant that changes to a product in a given period of time. So we have the measure of how fast and the amount of reactant that changes to product in a given period of time. The reaction rates can be controlled if we understand the factors that influence them. So how do we increase our rate towards products and decrease our rate towards reactants? When we talk about chemical reactions, we've sort of talked about them as this sort of magical black box factory, and we put our chemicals in, or elements in, they get smashed together automatically, and they get pumped out on a factory line out the door. And so they kind of get magically put together. We haven't talked about how that happens. One of the theories for how that happens is collision theory. So instead of this being a carefully assembled factory line, we have instead, we have our hydrogen, or iodine in this case, flying around, and when they happen to run into each other, if there's enough energy there, they will react. So we need collision energy, and our collision energy is related to particle velocity. So gas phase molecules have a wide distribution of velocities, right? We saw that that graph. I'm trying to reproduce it here. We had a graph like this, and it went something like this, and then it tailed off. And so this was velocity. We'll run over there. And this was, this was proportion. So this is like number of particles. And this is velocity. So we have a distribution of, we have some particles who are going really slow. We have some particles who are going really fast. And for a collision to result in a reaction, we have some threshold. We say that, okay, only collisions that happen in this region that are happening fast enough, those are the ones that react. So then, right, this wide distribution of velocities means that we have some that can react and we have some that can't. And then our high energy collisions lead to products, but our low energy collisions do not. So already you might say, okay, so if we, what we know about particle velocity is that it's related to temperature. So as we increase our temperature, we increase our particle velocity, and maybe that increases our reaction rate because we have more particles who are going fast enough. So that's the concept of activation energy. Most chemical reactions have this. They have this activation energy, or this energy barrier that must be overcome for the reaction to proceed. The activation energy may be the energy required to begin to break the bonds of the reactants. Then there are some factors that influence the rate of reaction, or the factors that influence the rate of reaction must be the same factors that affect the number of high energy collisions that occur per unit time. So if we're following this collision theory, then anything that affects the energy of the particles as they collide will also affect the rate of reaction. So one of these things is concentration. So the rate of reaction generally increases with increasing concentration of the reactants, because a higher concentration means more collisions. If you have more cars, I don't know if the car analogy works out very well here, but if you have more, let's just say you have people in a room, and you have the people walking around this room in straight lines, and whenever they run into something, they have to bounce off of it. If you have just 3 people in a big empty room, and they're walking around, just walking in straight lines, the odds of them running into each other are very low. Now, if you have a room, take that same room, and now instead of 3 people, you have 100 people in it, you can probably guess that a lot more people are going to be running into each other. And then if you want to factor in temperature to this, their speed can be varied. So you got some people who are walking, some people who are just running. You have some people who are, sort of jogging, and a variety of speeds. And you say, okay, for a reaction to take place, at least one person has to be running, or 2 people have to be jogging when they collide. This is the kind of demonstration you definitely do in, high school chemistry in the before times. I might have even made you guys do it in college. I think it's fun. But so as the reaction proceeds, what you observe is that the number of your reactants decreases, right? Because every time that they interact with each other and react, you've removed another reactant. So we can draw this graph, and we can say that the rate, so if this is our rate, and this is time, as our reaction goes on, we're going to see this decrease like this, so that the rate drops as our concentration drops, because we have fewer particles to react, um, and that's what this is showing over here on the right. If we have our, again, hydrogen and iodine, a low initial concentration, it means a slow initial rate. Intermediate initial concentration is an intermediate initial rate, and then high initial concentration is a fast initial rate. And those are relative to each other, at least in this regard. So the more concentration you have, the faster things can react, because the more often they collide with each other. Good test question there, by the way, right? Give these three: low initial concentration, intermediate initial concentration, and high initial concentration. Which one has the fastest reaction rate? The other thing, and we talked about this already a little bit, but the other thing that affects reaction rate is temperature. Because again, we're trying to get past that energy barrier. We need particles that are moving fast enough to react. So the rate of reaction generally increases with increasing temperature. So if we raise the temperature, we're making the molecules move faster, resulting in more collisions. And I guess to take this back to our classroom full of people analogy, if you had everybody running, you'd have a lot more collisions, even with just 3 people. So we went back to 3 people in the room, running in straight lines, bouncing off the walls. If they're running, the time it takes for them to collide is going to be shorter than if they were walking. So we get more collisions, and we get higher energy collisions, and so we get faster reaction rates. And again, right, low temperature, slow rate. Intermediate, high temperature, fast rate. So keep this idea of collisions in mind. Anything that's going to make things collide more often and faster is going to increase the rate of reaction. Did get a ping on Discord. Was it important? No, it was not important. Okay. I'm going to make sure it wasn't somebody trying to get into the lecture. Okay, so to summarize this collision theory, our reaction rates generally increase with increasing reactant concentration. They generally increase with increasing temperature. And reaction rates generally decrease as the reaction proceeds. And this makes sense, again, because as we proceed through the reaction, we're decreasing, so again, this is time, right? As the reaction proceeds forward, the number of reactants decreases, and then it's going to be basically the same exact chart, except instead of reactants here, it's going to be rate of, just use Rxn for reaction. So as we decrease our number of reactants, again, we're reducing the number of collisions, specifically collisions between the particles that can react, and that gives us a slower reaction rate. Okay, so this is a good one that we can do in the chat. So in a chemical reaction between 2 gases, you would expect that increasing the pressure of the gas would probably increase the reaction rate, decrease the reaction rate, or not affect the reaction rate. What do you think? If we increase the pressure of the gases. Okay, 1 vote for increase. Anybody else want to take a stab? Do you think that Mel is right? Do you think that they are wrong? All right, we got a thumbs up from Kaylee. Yeah, so if we increase the pressure, remember too that the partial pressure of a gas is related to the amount of gas. It's just related to the amount of gas. So as we increase the pressure, pressure is a function of the particles colliding with the sides of the walls. Pressure is also going to affect then the space in between molecules or atoms. So we're going to increase the reaction rate by increasing the pressure. So this again, now we're coming back to this idea of dynamic chemical equilibrium. So we um, talked about, right, collision theory. And so we got to keep collision theory in mind as we continue to talk about this. So a lot of our reactions are actually reversible reactions, which I mentioned before. They can proceed in a forward or reverse direction. So we can get this hydrogen iodide breaking back apart and going back the other way. And that is why we have this double arrow. That's what that double arrow is indicating. The condition in which the rate of the forward reaction equals the rate of the reverse reaction is called dynamic equilibrium. So the forward and reverse reactions are still occurring, but at the same constant rate. Concentrations of the reactants and products no longer change. Because if you think about it in a one-to-one sort of sense, when we get to the point where, let's say we get the hydrogen and the iodide, and that's going forward, and these are going forward at, let's just say, one reaction per, there's really not enough space for this. All right, let me zoom in here. So let's say we're going in the forward rate, so this top arrow, and this is going to be thinner pencil, one reaction per, let's call it a second. And so the backwards reaction then at equilibrium is also going to be one reaction per second. So that every second we've taken a hydrogen and an iodide and we've turned it into an hydrogen iodide. Should use this guy. And then every second we are also taking one of these and putting it back into I guess we're taking two of these and they're breaking apart again into the hydrogen and the iodine. If those reaction rates change, then we'll see some rebalancing. But again, since we talked about as the number of reactants decreases, the rate decreases. I guess I'm getting a little bit ahead of things, but we'll talk about that more in a second. So the concentration of reactants and products no longer changes. The reactants and products are being depleted at the same rate at which they're being formed. So an example up top here at 1 reaction per second. So we reach equilibrium, again, when the concentrations of the reactants and products no longer change. So we reach, and that's why it's called a dynamic equilibrium, because it's balanced, but it's only balanced as long as the reaction rates remain the same. So in this example here, again, we're using hydrogen and iodide, this reversible reaction. If we look over here, we can see in the first one, we have 8 hydrogens, 8 iodines, and 0 hydrogen iodides. In our second frame here at 15 minutes, we've gone 6, 6, and 4. And here, it tells us that we've reached equilibrium, but we know that because we have 4, 4, and 8. And then 15 minutes later, we still have 4, 4, and 8. So we've reached this dynamic equilibrium state. In this example, right, this is 4, 4, and 8. That doesn't necessarily have to be true. So the equilibrium can lie. It can be that there's the same number of moles on either side, but it could also be that there is way more products than there are reactants, or if a reaction doesn't occur very readily, there could be a lot more reactants than there are products. So the equilibrium does not mean that the concentrations are equal. It just means we've reached a state where they're no longer changing. So the concentrations of the reactants and products no longer change. Should make this a fatter highlighter. So let's use this example. We have Narnia and Middle-earth, and they're separated by this river. Narnia, in our first frame here, is pretty crowded. Some people like a crowded space, some people don't. So those people who don't like that crowded space are going to say, there's too many people in Narnia, look at Middle-earth. I can go over to Middle-earth, I get a nice large plot of land, I can maybe start a farm, I can have all the space that I want. So people start moving from Narnia to Middle-earth because they want to find more space. But as we move more and more people over to Middle-earth, Middle-earth becomes more crowded. And at some point, the people who are over in Middle-earth are going to say, wait a second, this is crowded over here now, it looks like there's more space over there in Narnia. So you're going to have people going from Middle Earth back over to Narnia. And what will happen is, at least in this silly example, is that the rate of people moving back and forth will eventually balance out. So there will be the same number of people trying to move to Middle Earth as there is the number of people trying to move to Narnia for a whole variety of reasons. But that's when we've reached this dynamic equilibrium. Okay, where's this? I forgot to prep this video. Let me go find this video. Okay. I come over here. And let's just... We're not going to watch this whole thing.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now, the number of limb transfers per second forward will start high and then fall, and the number of limb transfers per second backward will start at 0 and then rise. Eventually, they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
All right, I guess I was wrong. We were going to watch the whole video. It wasn't too long. That example is supremely bizarre, but I think that helps with remembering it. Right. So that's basically everything that we've covered. Also, I do want to mention at this point, I'll put a link to it in the description of the YouTube video. Again, I think most people know who Hank Green is now. He's blown up a lot on TikTok. He has a YouTube channel called Crash Course, and there is an entire Crash Course chemistry playlist. And Equilibrium is one of those videos. And so if you're struggling with the concepts especially, that's a great place to go to get another take on these concepts. And probably a more entertaining take. I don't know. I won't say. I think Hank Green's a pretty entertaining guy. So then, right, our equilibrium, at equilibrium, the rates of the forward and reverse reactions are equal, not the concentrations. So what can we know about the concentrations, or what can we know about the concentrations and reactants of products? Well, we have the equilibrium constant, which is a way to quantify the relative concentrations of the reactants and products at equilibrium. So our equilibrium constant is built from our balanced chemical reaction. So for this generic chemical reaction here, you can see that we have these are our coefficients, and we take those coefficients and we have the molar concentrations. These are the molar concentrations, or the concentrations of our products, and we raise each of these products and reactants to the power of their coefficient. So this equilibrium constant is the ratio at equilibrium of the concentrations of the products to the reactants. So we'll see that more specifically here. So if we write an equilibrium expression for this reaction, right, we have N2O5 decomposition reaction into nitrous, NO2, and oxygen. And so when we write our chemical equilibrium equation, you can see that we have our products on top, or the numerator, raised to the power of their coefficient. And so if there's 1, that's an implied, and we also don't write that down here. And then on the denominator, we have our product, or a reactant, raised to its coefficient. Not too hard, just got to remember where things go. We're really just rearranging our chemical equation into a expression that tells us the equilibrium. So let's write an equilibrium expression for this chemical equation. So we're going to have K EQ, and that's going to be, again, our products over our reactants. So we can do hydrofluoric acid over, the brackets are important, right? Brackets represent molar concentration. And then we'll have H2, and because we're multiplying, it doesn't matter the order of these in the denominator, but it can be convenient to follow the same order that they are in the chemical equation. And then we just raise each of these to the power of their coefficient. So for hydrogen and fluorine, those both have a coefficient of 1. But for hydrofluoric acid, we have a coefficient of 2. So we're just raising it to that power. When our equilibrium constant, KEQ, is large, the forward reaction is favored, and there will be more products than reactants at equilibrium. When KEQ is small, the reverse reaction is favored, and there will be more reactants than products at equilibrium. I think we're going to have an example of this that sort of makes it a little bit more clear why that is. It's important to note that these equilibrium constants are at a specific temperature, because we'll see, and as we've talked about a little bit, temperature will affect the rate of these reactions and can push it in one direction or another. So temperature is important. So we have a large equilibrium constant. We can look at this and see that we're taking our hydrogen, combining it with bromine to make 2 hydrobromic acids. And if we count these, we can actually just count these and say that there's, how many? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrobromic acids. So if we say that there's 11 hydrobromic acids, and then we have 1 H2, this is 1 H2, 1 hydrogen, and you have 1 bromine. So multiply those together, and then this is squared. Of course, very simplified here. You actually want to use the molar concentrations when you do this. But 11 squared is, I believe it's 121. So we have 121 divided by 1. So we have a large equilibrium constant. I have to grab my calculator. But I'll do that when we get to a problem that I need the calculator. So if we have 121, that means we have 121. Well, it doesn't mean we have 121, but that means that we have a lot more products than we do reactants. So here we have an example of what a small equilibrium constant would look like. And again, we're given the equilibrium equation here. And we have, go through and count these. For nitrogen, let's count nitrogen first. 1, 2, 3, 4, 5, 6, 7. So we have 7 nitrogens. And then for oxygen, we have 1, 2, 3, 4, 5. And then for our NO2, we have just 2. Now this is 2 squared. But if we take our 2 squared, that's 4 divided by 35. So this is going to be a small number because we're doing 4. Let's take a calculator here. 4 divided by 35 is 0.11. So this would be equal to 0.11. And that's a small equilibrium constant. So we know that the reactants are going to be favored. So just summarize the significance of this equilibrium constant. The reverse reaction is favored when KEQ is much less than 1. The forward reaction does not proceed very far. So we get a few products, but not very much. If KEQ is about 1, neither direction is favored. The forward reaction proceeds about halfway. So significant amounts of both reactants and products are present. If KEQ is much larger than 1, then the forward reaction is favored, and the forward reaction proceeds virtually to completion. And you might ask, well, what does about 1 mean? There's probably anywhere from really like 0.5, probably up to 2 is kind of fairly balanced. That's fairly in the middle. It's not exactly clear. You'll see though when we talk about KEQ being much less than 1, we're usually talking about 10 to the minus 5 or less. And we're talking about it much greater, we're talking 10 to the 5 or greater. So we're talking about much greater or much less. And we'll see how that happens as we do some examples. Probably 10 to the 3 is probably more of the range. Okay. So things get a little bit squirrely when we start working with solids and liquids. So if we have a pure solid or a pure liquid, those are excluded from the equilibrium expressions because they are constant. So if we have calcium carbonate, solid, decomposing into calcium oxide, another solid, plus CO2, since calcium carbonate and calcium oxide are both solids, they're emitted from the equilibrium equation, or equilibrium expression, and our equilibrium is only dependent on the concentration of CO2. So this is why it's important to write out what phase these are in. So the things that we are going to include in our equilibrium expressions are aqueous and gases, not solids. Let me do these in a different color. Solids or liquids, which is sometimes written as a cursive L, sometimes it's just L. Usually for handwriting, you write it as a cursive L because you can't italicize it. So let's write an expression for this. So if KEQ equals, and I'm just going to throw the line in to start with. You can see that H2O is a liquid, so we're not going to include H2O. But we are going to include hydrochloric acid, oxygen, and chlorine, because those three are gases. So we have products over reactants. So we have Cl2. And that's going to be raised to the second power because its coefficient is 2. And then for our products, or reactants, excuse me, we'll have HCl raised to the 4. And then we'll have oxygen raised to the 1. So we leave that out. That's implied. All right. Nothing too difficult yet. Sorry, I said yet, but none of this is too crazy. A lot of concepts here today. There will be some problems for determining what the equilibrium constant is, and also using the equilibrium constant to find other concentrations. So, right, we talked about our dynamic equilibrium, and we talked about collision theory, and we saw that temperature is temperature is important to reaction rates, because if we increase the temperature, we increase the speed of collisions, and we increase the likelihood of a collision in the first place. So temperature is often specified, but is not part of the equilibrium expression. So we would say that this is the equilibrium constant at this temperature, right? So before it was at 25 degrees C. Sometimes it could be specified at other temperatures, but it's not part of the equilibrium constant. The concentration should always be in moles per liter, or molarity. We don't write those units for the equilibrium constant because they get a little bit weird when you do the dimensional analysis. You're going to end up with, sometimes they cancel out, which is nice because it should be unitless. Sometimes you're going to end up with moles cubed per liters cubed, or liters per moles, in weird units. So we leave the units off of our equilibrium constant. The concentrations for these equilibrium will not always be the same, but the equilibrium constant is the same at a given temperature. So the ratio between the two things will always stay the same. And that's what the equilibrium constant is it's a ratio between products and reactants. So let's consider this reaction. Again, we've got our hydrogen and our iodine. They are reacting to form hydroiodic acid. So we've got this mixture that comes to equilibrium at 445 degrees C. The measured equilibrium concentrations are 0.11 molar, 0.11 molar, and 0.78 molar. What is the value of the equilibrium constant? So we've been writing these out, and nothing changes here. We'll say their KEQ is equal to, here, let me move this over to the side a little bit, because what I'm going to do is first I'll write out our general for this reaction. So I'll have hydroiodic acid, because that's our product, raised to the 2, because we have a 2 coefficient here. So it becomes our exponent. And then we'll have the concentration of H2 and the concentration of I2. And just to make sure, we want to come back and check that we do indeed have gas, gas, and gas. So we're not working with any liquids or solids. So now we can just fill in the values that we were given for each of these concentrations. So we have H2 is going to be 0.11 molar times I2, which is another 0.11 molar. And then we have our 0.78 molar squared. So we just do the math. Oh, this is where I need my calculator. All right, I'll be right back. Okay. Alrighty, so we'll do 0.78 squared divided by 0.11 times 0.11. We should get 5 5.0, well, I guess 5.0 is going to be our KEQ at 445 degrees C. So you can see that the products are favored over the reactants. They're not greatly favored over the reactants, because you can see that as a proportion here, we've got about 1/7. So we still have about 14% of each of our products when compared to the reactant. So, or each of our reactants when compared to the product. So it's not a hugely favored reaction for the products, but it is greater than 1. So it is product favored. These are just some. Oh, again, this is to compare for these reactions, for this actually specific reaction that we just did, what the equilibrium ends up being based on different starting amounts. So if you take an empty flask, an empty sealed flask, and you put 0.5 molar H2 and I2 at equilibrium, you'll get exactly what we saw. You'll get 0.11, 0.11, and 0.78. Oh, I'm sorry. This is 50, the decimal place there, so it's not ambiguous. Right, so 50. Even more favored than before. Okay. Switch my calculator to scientific. Mode. Change it back. Okay. Anyways, so you can see that at equilibrium, this is the one we just calculated, we have an equilibrium constant of 50. If we just take 0.5 molar hydroiodic acid, or hydrogen iodide, I suppose, since it's a gas, it is still an acid. So if we just take our gas and put it in this empty flask, and we let it go to equilibrium, we're still going to get 0.055 of each of our reactants. So some of this HI will decompose into our reactants. And if you do the math for that, you still get 50 as the equilibrium constant, all at the same temperature, of course. And you can keep going down this list. No matter what you add to this flask, eventually it will find its equilibrium, and that equilibrium constant will be the same, as long as we're at the same temperature. The amounts of these will change, right? So here we have one of this, 0.5 molar of this, the iodine. And so these concentrations don't end up being the same because we started with different amounts, even though all of these were the same. We still end up with 50 as our equilibrium constant. Okay.
So is that just because you can change the reactants, but then the product has to balance out?
It's because it will find. You can think about it like it'll find where the equilibrium is. So it'll always produce. Essentially, what this is saying is, yeah, no matter if you put whatever amount of reactants you put in, they will combine to form a number or an amount of products, so that this equation equals 50.
Cool. Yeah. So the product is going to be a ratio of the reactants, and then that equilibrium constant remains the same.
Yes.
Cool.
Yeah, exactly. Okay. The ratio will always be the same at the same temperature. So if we've got a mixture, carbon monoxide and hydrogen. Okay, so we've got a mixture of carbon monoxide, hydrogen, and methanol that's allowed to come to equilibrium at 225 degrees C. The measured equilibrium concentrations are 0.489, 0.146, and 0.151. What is the value of the equilibrium constant at this temperature? Again, this is just like that other problem. So we've got KEQ. Again, just for the sake of clarity, I'll write these out. CH3OH. And our coefficient there on, coefficient's 1, so exponent of 1. Carbon monoxide, again, coefficient of 1. And hydrogen, gas, coefficient again of, coefficient now of 2. Because of coefficient 2, so exponent of 2. And then we just fill in the numbers that we were given. .489 times 0.146 raised to the second power, 0.151. Easiest mistake to make on these problems is to forget those exponents, for sure. Ooh, the upstairs neighbors are being stompy today. So we're going to take our 0.151 divided by 0.489, and then 489 times 0.146 squared. Also, when you're entering these into the calculator, they can get a little bit, you have to make sure that you do it sort of in the right order. I can explain more about what I mean about that if somebody wants me to, but order of operations is important. Yeah, I'll do 3 digits. So that's 14.5 is our KEQ at 225 degrees C. Cool. All right, so I mentioned this, but we can use our KEQ to calculate equilibrium concentrations of one of the reactants or products. So if you're given if you're given all but one of your reactants or products and the equilibrium constant, you can calculate that missing number at equilibrium. So if we have this reaction at equilibrium, we're given a concentration of, I don't even know what to call that, COF2. And then it's decomposing into carbon dioxide, carbon tetrafluoride. What is the concentration of CO2 at equilibrium for this reaction? So let's just first set up our equilibrium equation. So KEQ equal to products over reactants. So we'll do CO2, CF4, and then on the denominator we have our reactants, COF2 squared, again, coefficients, right? So these each had a coefficient of 1, so I just left those as that implied 1. And now we can fill in the numbers. So our equilibrium constant is 2. We are looking for carbon dioxide. Usually when I do these, I'll fill that in with X because it's easier to write. But then we have our carbon tetrafluoride, 0.118. Don't know what that sound was. And then we have our reactant, 0.255 squared. So now it's just a little bit of algebra, and we can rearrange this to solve for CO2. Let me zoom in here so I have, so this will end up being 2.00 times 0.255 squared divided by 0.118 will equal concentration of CO2. Squeeze it in there. So I'll do 2 times 0.255 squared divided by 0.118. So our concentration of CO2 then is 1.10 molar. Now they're vacuuming upstairs. That's fun. Okay. Are there any questions about that? Very helpful to make your first step to write out whatever the equation is if it's not given. Then you can fill in your numbers that you do have, and that'll usually show you pretty quickly how to get where you're going. So we have diatomic iodine, decomposes at high temperatures to form iodine atoms according to this reaction. In an equilibrium mixture, the concentration of I2 is 0.1 molar. What is the equilibrium concentration of I? So the individual iodine atom versus the iodine diatom. So again, we just start out by writing KEQ equal to products over reactants. It's another spot where you can get tripped up. So this is our iodine, our equilibrium constant of 2, or not equilibrium constant, our coefficient of 2 becomes our exponent, and then it's just the concentration of I2 on the denominator. So if we fill in these numbers, we'll have our KEQ is equal to 0.011, and that is equal to 0.10 squared over I2. Wait, did I do that right? No, I did that backwards. The sounds coming from upstairs are distracting me. 0.10 I squared. Again, just a little bit of algebra. And so what we'll end up getting is the square root of 0.011 times 0.10 equals the concentration of I. So 0.011 times 0.1, that. So you can do either the square root or you can raise it to the 1/2 power, or the 0.5. And our iodine concentration is going to be 0.033 molar. The trick question that might be written out of these, not saying I'm going to write one, I'm just going to say it's a possibility. I don't think I will. But the trick question that you could write for this is, given this molarity, given this KEQ at a temperature, what is the concentration of this at a different temperature? We don't have a way to solve that. So the answer would be not enough information. Just saying. That's the kind of trick question that would be written for one of these. Okay, so we've talked about when we do get to equilibrium, but what happens when we take this equilibrium and we disturb it in some way? And I don't mean by disturb, I don't mean by showing it the Salad Fingers video, or creepy videos on YouTube, or creepy pasta off of Reddit. But what we mean is adding more reactants or adding more products, maybe changing the temperature. How can we shove this equilibrium? How can we give it a push? And where does it end up after it settles out again? So a system at equilibrium fights back when disturbed. So if you do disturb it in some way, it will go back to, I just dropped my pencil. It'll go back to its equilibrium. Okay, so let's go back to Narnia and Middle-earth. Narnia and Middle-earth now, they've reached a happy equilibrium since we left them 20 slides ago. They've balanced out. They've got the right number of people in Narnia, they've got the right number of people in Middle-earth. There's still some people who are shifting back and forth, depending on how the economy changes. But this causes, so let's say we add, though, a population to Middle-earth. Sauron's just spawned a bunch of Uruk-hai, to show you how nerdy I am. Anyway, so we've added a bunch of Uruk-hai. The population, suddenly we have this huge population boom in Middle-earth. How is this going to affect this equilibrium? Well, because we've added more people to Middle-earth, we're going to get more people who are going to want to leave Middle Earth because it's now too crowded for them. So they're going to balance back out, and the system's going to respond by shifting to the left towards Narnia. We're going to shift more people from Middle Earth to Narnia. So what would happen if suddenly there was a war in Middle Earth and there were a lot fewer people? If we removed population from Middle Earth, we would probably see a shift from more people shifting from Narnia to go to Middle Earth to fill in that empty space. As tragic as it is, there are empty homes there, and the market prices are low. Maybe the interest rates are high, so people are trying to sell. I don't know. So it shifts, though, to the left. So basically, this equilibrium is going to move depending on how we add it. So if we add something to one side, it's going to shift to balance that back out. Again, to get that same ratio and maintain that ratio in the equilibrium constant. So when product is added to an equilibrium, the rate of the reverse reaction increases. Again, think back to collision theory. If we add more of our products, that is more molecules that can either decompose or react in the opposite direction, so that rate is going to increase, and that will shift our reaction to the left until those rates have again equalized. So if we add product, the concentration of product will be too high, our ratio will be too high, and it'll shift back down. So here on the left, we're adding more N2O to this reaction. And so then we've disturbed our equilibrium, and then our rate of reaction is going to shift back to the left. I'm not a big fan of this figure. It's not super clear. And the reverse happens, or the opposite happens, I should say, when we add more reactant. So if we add more reactant to the reaction, again, we've increased the number of molecules that can form product. We've increased our concentration of our reactants, and so that's going to increase here. I should turn this way. If these are our reactants, I guess on the video it's this way. So if we have our reactants here, we've increased them, that concentration is going to be too high, and that rate's going to be higher, and that will slowly come down, or quickly come down sometimes. It'll come down, though, so that the rates of the forward reaction are the same as the rates of the reverse reaction. And so our reaction shifts to the right. Again, so here we're adding more N2O. These are N2O molecules. And as we add them, we have more molecules that can split apart, and the shiftum is going to shift to the right because we added N2O, more of those are going to decompose. We're going to end up with more NO2 as well. So if we've got a chemical system at equilibrium, increasing the concentration of one or more of the reactants causes the reactant to shift in the direction of the products. Increasing the concentration of one or more of the products causes the reaction to shift in the direction of the reactants. So adding something is like giving it a shove. So if we add reactants, we're shoving it from the reactant side. Write this down. We are reactants to products. If we add to the reactants, that will overflow into the products. And so we'll increase the products, and we say that the reaction shifts to the right, shifts to the products. If we do the opposite and we add to the products, those products then will overflow into the reactants, and we say that the reaction has shifted to the left. Let me see here. Okay, we'll do this example and then we'll take a break. Let's consider the following reaction in a chemical equilibrium. We have two BRNO, and we have N2 or 2NO and bromine. So what is the effect of adding more bromine to this reaction mixture? Go ahead and type in the chat what you think is going to happen. If we add more bromine, Br2, which direction are we going to shift? We're going to shift left to the reactants, or we're going to shift right to the products? One vote for left. If there is no dissent, we shall proceed. Yeah, so we've added more to our products, and because we have extra products now, those are going to overflow back into our reactants. And so what happens then if we add more BRNO? We're going to shift left or right?
Right.
Right is right. We're going to shift over to the right again because we got more products than we do reactants, and so that's going to overflow into the other. And then if we remove, so we talked about adding either way, but if we remove some of our Br2, which way are we going to shift?
To the right.
To the right again. Because what matters is the proportion. So if we remove some of our Br2, we now have more of our reactants than we do of our products, and that's going to shift this equilibrium. Should write these in left, right, right. Okay, we'll leave it on this slide. We'll take a short break. Be back at 11:05 or 11:07. 11:07. 5-minute break. Okay. Swap the coffee out for the water. Here we go. So we looked at now if we add or remove products or reactants, how that affects the equilibrium. But now we're going to look at changing the volume of a gas and how that changes the pressure and how that changes the equilibrium. So if we decrease our volume, we increase in pressure. So we're taking that plunger and we're pushing it down. We're making the gas more compact. So we're pushing those atoms closer together and we're increasing the pressure. If we do the opposite and we take our then gas and we pull the plunger up, we've expanded it, we've made a larger space, and that's more room for the atoms or molecules to be flying around in, and we decrease the pressure. So lowering the number of moles of a gas results in a lower pressure at constant temperature and volume. Lowering the number of moles in a gas results in a lower pressure and constant temperature and volume. And so we can relieve the pressure change in a system by changing the moles of a gas. So let's say we decrease our volume. We've increased the pressure. The atoms and molecules in the system, they don't want to be at this high pressure. So to bring the pressure back down, the equilibrium will shift to the side of the reaction with fewer moles of gas. So let's zoom this in here. So we can see that on the left side, we have 4 moles of gas. And on the right side, we have 2 moles of gas. So to shift our equilibrium to relieve pressure, we want to take these 4 moles of gas and convert them, 4 moles of gas, and we convert them into the 2 moles of gas. So by increasing our pressure, we have more products. And that shifts our reaction to the right. Decreasing volume increases pressure. To relieve that pressure, we convert our atoms or molecules into whichever side has fewer moles of gas. If we do the opposite, an increase in volume decreases the pressure. And if we decrease the pressure, we're actually going to form more moles of gas to counteract that pressure change so that the atoms and molecules don't feel too lonely. So we're going to go from, again, we've increased our volume, decreased our pressure, and to fight that change, we're going to take our 2 moles of gas and we're going to break it apart into our 4 moles of gas, which shifts our equilibrium to the left. Sorry, it shifts our reaction to the left. So we'll form more particles of gas to help fill that space and get back to the pressure that it was before the change. So to summarize volume, if we're at equilibrium, decreasing the volume causes the reaction to shift in the direction that has fewer moles of gas particles. Decreasing volume, we want fewer gas particles because we've increased the pressure. If we increase the volume, then we cause the reaction to shift in the direction that has more moles of gas particles because we have decreased the pressure. So increase the volume, more moles of gas. Decrease the volume, fewer moles of gas. And if the moles of gas particles on both sides of the chemical equation is equal, the change in volume has no effect. So if we had something like the N2O2 in equilibrium with NO, I guess that's 2NO. I was trying to think of an example that would be more balanced, but I think, maybe H2 plus I2 is 2HI. So in this equation, we have 2 moles of gas, we have 1 mole of hydrogen, 1 mole of iodide, and then we have 2 moles on this side as well. So 1 mole plus 1 mole is 2 moles, and then we have 2 moles on this side. So changing the volume for this reaction would have no effect. It would just stay the same. All right. So let's consider this reaction. We have 2 SO2 and plus oxygen, O2, and we're going to get 2 SO3. So if we decrease the volume in the reaction mixture, which way is our reaction going to shift? We're going to shift left or right. Left or right. So the first thing to do for this equation is to count the number of moles of gas on either side. So on the left, we have 2, and then we have, right, implied 1. So we're going to have 3 moles. And on the right side, we only have the 2, so we have 2 moles. And if we think about this in step, we've decreased the volume, which increases the pressure. So to relieve that pressure, we want fewer moles. So then we want to decrease moles of gas. So we're going to shift this to the right, because we have fewer moles of SO3 than we do, or products, than we do of reactants. If we increase the volume of this reaction mixture, increase volume, that's going to decrease pressure. So we want to add more moles of gas to fill in that extra space. So we want to increase moles. So we're going to shift this reaction to the left then, because we have more moles of gas in our reactants than we do in our products. Any questions about that one? Cool. So now we've looked at adding or removing products and reactants, how that affects the equilibrium. We've now looked at volume and, by extent, pressure and how that changes. Now we're going to look at temperature. Temperature and which way we're going to be moving that is dependent on if we have an exothermic or an endothermic reaction. So in an exothermic reaction, we can think of heat as a product. So if we raise the temperature of an exothermic reaction, it's like we're adding more heat to the product side, and the reaction will shift to the left. So if you wanted to write out something like CH4 plus O2, right, our basic combustion reaction. For the sake of this, we'll assume that we can unburn our CH4. Combustion reactions are not reversible. But just for the sake of this, because it's an easy one and has heat, we'll have CO2 plus H2O. And if I want to balance this, I put a 2 here and a 2 here. But then we can also think as heat. So delta means heat. Heat as one of our products. In an endothermic reaction, we can think of heat as a reactant. And so raising the temperature of an endothermic reaction is like adding heat to the reactant side. The reaction will shift to the right. I cannot think of off the top of my head an endothermic reaction specifically. But let's just use, right, so if we have delta then plus A in our endothermic reaction, and this gives us B plus C, to just use some generics. So you have this decomposition reaction that requires heat. And so if we increase the heat, we're increasing the reactants and thus forming more products and shifting to the right. So here we have exothermic reaction. Again, heat or delta. If we're adding heat, into this exothermic reaction, we shift to the left. If we remove heat, so we start cooling this reaction down, we're removing this heat, our reaction will shift to the right to make more of our products. For our endothermic reaction, the opposite is true. Because we have heat as one of our reactants, when we add more heat, that shifts us to the right. And when we are removing heat, the reaction shifts back to the left. So this is that reaction from the previous. If we have our warm NO2, we have mostly, so we're adding heat. For this first one, we're adding heat. And so that shifts us over to the right, so we get this brown NO2. But if we remove heat and we chill this, so we're taking heat out, then we're shifting our reaction to the left because we're removing one of our reactants. And we get the clear N2O4. So temperature change is one of the simpler ones. You just have to identify whether you have an exothermic reaction with heat as a product. So in an exothermic reaction, if we increase the temperature, we cause the reaction to shift to the left because we're increasing one of the products. If we decrease the temperature, we cause the reaction to shift to the right because we are removing one of the products. And for an endothermic reaction, we have heat as a reactant. So if we remove reactants, or if we remove heat in this case, then we shift the reaction to the right. Sorry. If we remove heat, we shift it to the left. If we increase the heat, we shift it to the right. Because the increasing temperature, shift to the right. Decreasing temperature, shift to the left. Increasing temperature when we have an exothermic, shifts to the left. Decreasing when we have exothermic, shifts to the right. Just think of it as a product or a reactant depending on which reaction type you have, whether it's endothermic or exothermic. So we're given here. The following reaction is exothermic. So the first thing that I want to do when I see a problem like this is I will write plus heat. So what is the effect of increasing the temperature of the reaction mixture? So if we think of this, we've been given that it's an exothermic reaction. And we see that heat is one of our products. If we increase temperature, we are
Shifts left.
increasing heat, and we shift left. And if we decrease temperature, we're removing that product. And so we shift
Shifts right.
to the right. Exactly. Okay. So now we've talked about equilibrium constants. We've talked about what equilibrium is, a dynamic equilibrium. And we've talked about all of the things that affect equilibrium: temperature, pressure, number of moles of products or reactants. Another process that takes place in an equilibrium is solubility. So the solubility, KSP, is the equilibrium expression for the chemical equation that represents the dissolving of an ionic compound. So again, we're removing solids from equilibrium expressions as well as pure liquids. If we have a large KSP, that means that the compound is very soluble. If we have a small KSP, that means that the compound is not very soluble. That'll make more sense when we see one. So we write the equation, the chemical reaction. We write it with its, basically the net ionic equation here. So we write the equation for the chemical reaction showing the solid compound in equilibrium with its dissolved aqueous ions. And then we write the equilibrium based on this equation. So we're basing it off of really the net ionic equation for the compound dissolving in the liquid. So we get barium 2+, and we get sulfate 2-. And that's our KSP. And you can see that, again, we've excluded barium sulfate from the KSP. And again, if it's products over reactants, again, then the implied here is that it's over 1. So if these numbers are large, if our barium and our sulfate concentrations are large, then we'll have a large KSP because most of our barium sulfate is dissolving. If these are small, then we know that none of the barium sulfate or none of our solid is dissolving and creating ions in the solution. So these are some KSPs for various compounds. You can see there's a wide variety. But if you look at these, something like copper sulfide is 10 to the minus 36, which is an incredibly small KSP. So almost none of it is being dissolved, assuming that this is in water. But we have other ones where, and none of these are very soluble. The 10 to the minus 5 looks like our most soluble compounds. But even those are going to be considered insoluble. But we can calculate exactly how much is present for each of these based on those KSPs. So you could calculate for copper sulfide, even though it's incredibly insoluble, you could calculate exactly how much of it would solubilize. So let's write KSP expressions for each of these. So we have silver iodide. I'm just going to write it right off of that. And so we're going to break this down into its ions. Ag plus I minus. These are both aqueous. So our KSP is just based on those ions. So we're going to have Ag plus multiplied by the molar concentration of I minus. And that's it for for the KSP for silver iodide. For calcium hydroxide, again, write out what the ions are going to be and balance it. So Ca2 plus 2 OH minus, because we have 2 hydroxides. And so our KSP then is going to be Ca2 plus molar concentration and the OH minus molar concentration. And just like with our other equilibrium constants, we're going to take that 2 and use it as an exponent. So the solubility of a compound is the amount of compound that dissolves in a certain amount of liquid. We call this the molar solubility. The molar solubility is the number of moles of compound that would dissolve in 1 liter of solvent. We can calculate this molar solubility from KSP, and we abbreviate molar solubility as S. Hi. I made a mistake when I was talking about using KSP to determine molar solubility. I'm just going to rework these problems. The apology is mostly for those who watched the lecture live or who watched on Zoom. So if we have our silver chloride solution here, we can write out our KSP equation. KSP is equal to the concentration of silver plus times the concentration of Cl minus. And then we set 1.77 times 10 to the minus 10 equal to Ag plus and Cl minus. Now, because these are occurring each in a 1-to-1 ratio from the silver chloride here to the silver and the chlorine, these can be rewritten as X times X, because the concentration of each of these will be the same. And so we can do our X times X, and this is the same as the video that I recorded live. And so we'll then get 1.77 times 10 to the minus 10 is equal to x squared. And if we take the square root of both of those, S is equal to 1.77 e to the negative 10 raised to 0.5, or 1.33 times 10 to the negative 5 molar. So that is our molar solubility of silver chloride. For this next problem, again, we're not going any more complicated than a 1-to-1 ratio for these questions. So we're going to have calcium sulfate in equilibrium with Ca2 plus SO42 minus. Now to solve this, we need the KSP. So go back over to this table, and I have it boxed in here, calcium sulfate, 7.1 times 10 to the negative 5. So I'll write that 7.10 times 10 to the negative 5 is equal to KSP. So then to calculate our molar solubility, again, we just do KSP. We want to write out our solubility equilibrium equation here. We're going to do Ca2 plus times SO42 minus. Right, and so then we just set this equal to 7.10 times 10 to the minus 5. And that's going to be equal to, again, because these occur in a 1-to-1 ratio with calcium sulfate, we're going to get the same amount of each. So we can replace these with X times X. And the same thing as the other problem from here on out. And that's going to give us X squared. We take the square root of 7.10 times 10 to the minus 5 is equal to square root of X squared. And that will give us 7.1 e to the minus 5 raised to the 0.5. And that's going to be 8.43 times 10 to the minus 3 molar equals S. So if you wanted to, then use, do a problem where you have more than a 1-to-1 ratio. So let's use this example again of potassium iodide. Or sorry, not potassium iodide, calcium iodide. What you would do is you would again write out your ion equation, 2 plus 2 I minus. So now when we write this problem down, I'm just going to make up a KSP for this. We're going to call it, again, this is made up. Don't know if it's exactly true. Don't know if it's true at all. We're going to use 3.5 times 10 to the minus 7. All right, it's not very soluble. But our equation, then, we're going to write it out the same, KSP, at least to begin with. KSP is equal to our calcium 2 plus multiplied by our I minus squared. But the key difference here is that when we look at how we're going to be going from our calcium iodide to our calcium and our iodine, or iodide, we're going to get 1-to-1 going from calcium iodide to the calcium ion, but we're going to get twice as many iodide atoms out. So then, probably move this too far down. So what we want to do is then we want to replace then our calcium with X, and we're going to replace our iodide with 2X. So we'll still get KSP is equal to X, but now we'll get multiplied by 2X squared. And this is key here, that the squared goes outside of these parentheses, because then KSP is equal to X times 4X squared, because that exponent gets applied to everything inside. And then KSP is equal to 4X cubed. So then we can take our KSP from up here, plug this in, 3.5 times 10 to the negative 7 is equal to 4x cubed. Divide both by 4, so we'll do 3.5 times 10 to the minus 7 divided by 4. We're going to get 8.75 times 10 to the minus 8 is now equal to x cubed. And then we can do 8.75 times 10. We'll take the cube root of everything. And part of how you do that is to raise this to the 1/3. It's one way you can type it into your calculator to get x. And so we'll take that result and we'll raise it to the 1/3. And we'll get 4.44 times 10 to the negative 3 as, or I should say molar, as S, or our molar solubility for calcium iodide. All right. I apologize for any confusion that may have caused, but again, we're going to keep it simple for this class. Part of the logic to get here is ice tables. Anyways, I will send you back now to the live lecture. Molar solubility. So we talked also, right, so we've talked about a bunch of stuff here, because again, we're covering a chapter a day, but go way back, we talked about there needs to be a certain amount of energy in our collision theory for two particles to react, two atoms, two molecules, whatever they may be. We call that energy the activation energy, or the activation barrier for a reaction. And that is the amount of energy we need to have for the reaction to take place. And activation energies exist for most chemical reactions because we have to break the original bonds before we can form new bonds. So at a given temperature, the higher the activation energy for a chemical reaction, the slower the reaction rate. So the higher this hill, so if we have the energy of our reactants, the energy of our products, the difference between these two is our activation energy. If this activation energy is higher, that reaction is going to proceed slower because there are going to be fewer particles that have the required energy to make it over that hill and fall back down to the lower energy of the products. So we have some ways then to speed up if we have a slow reaction and we want it to go faster. One of those things is we increase the concentration of the reactants, which increases our collisions per unit time and the probability that they have the energy to overcome the activation barrier. We can also increase the temperature, which results in more collisions per unit time and also results in higher energy collisions. Or we can use a catalyst, which lowers the activation energy barrier. And depending on the reaction that you're working with, you may want to use 1, 2, or all of these. But you can see how if we increase the concentration of the reactants, maybe our reaction, we don't have a lot of reactants to add. Maybe we've got a limited number of reactants, so that's not a great way to add them. If we have a exothermic reaction, if we increase the temperature, we're also adding to our products already. So that could actually hinder, depending on where the equilibrium's at, that could hinder our reaction because we're adding to the products, so you wouldn't want to use heat to increase the rate of your reaction. So when either of those two things doesn't work, then a catalyst is a great option to lower that energy barrier. You can think of the energy barrier as a hill, and so to get over that hill, you need to have the right amount of energy. So we can increase the reaction rate by pushing these boulders harder up the hill. If we increase the temperature, right, we add more energy. Or we can find a path that goes around the hill and take a different path. And that's what the catalyst essentially is doing. It's taking that energy barrier and it's circumventing it. We're finding another route that we can take to get to our reactants without as much energy. So a catalyst is providing this alternate pathway with a lower activation energy for the reaction. Should be a slide about this. I guess there's not a slide about this. The only thing that a catalyst doesn't do is change the equilibrium. It changes how fast we get to equilibrium, but it doesn't change the equilibrium. We're still going to get the same proportion. Our KEQ is going to be the same. The only thing a catalyst does is change how fast we get there. I'm going to write that on the slide. only affect how fast. Okay, there we go. All right, they only change how fast we get there. In biology, there are lots and lots of catalysts. In fact, we couldn't exist without catalysts. Enzymes are biological catalysts because many reactants are thermally sensitive. So if we increased the temperature, we would destroy those catalysts or we'd destroy those reactants. So the only way to carry out many reactions is to use catalysts. Most of the thousands of reactions that occur for living would be too slow at normal temperatures. So our bodies have evolved enzymes to catalyze these biological reactions so that they can increase the rate. Sucrase is a catalyst. It creates a pathway with a lower activation energy for the conversion of sucrose to glucose and fructose. So lowers this energy so that we can break those two apart. When sucrose is in the active site of this enzyme catalyst, the bond between glucose and fructose weakens, which lowers the energy of activation for the reaction and increasing the reaction rate. So these enzymes are really, really cool. They're proteins. So as you can see here, let's see if I can pick out which one of these. One of these is sucrose, or one of these is glucose, and the other one's fructose. And so what happens is when the sucrose gets into this pocket on the enzyme, that pocket opens up a little and stretches that bond so that it's easily broken. And a lot of these enzymes have very specific sites, and when a molecule is inserted into it, it undergoes a change that helps change that molecule in whatever way your body needs it to be changed. Okay, so that is it for this. That is chemical equilibrium. Let's see. I will reiterate again. We have a test on Friday. This is exam 4. Test will again be available from noon to 6 p.m. Going to shoot for around 50 questions again and about 100 minutes. I think we've hit a good balance there for the time. I might increase the time depending on how many calculation problems there are. Make sure you go back and look at previous exams for questions that I've repeated, or question types that I've repeated, because those will probably be repeated on the exam, on exam 4. Also, exam 4 will replace your lowest score if exam 4's score is higher. So if you get a 90 on the exam and your lowest score was a 60, congratulations, you've got a 90 for that 60 now. So this test could be a big swing for your grade. Could help you out a lot. And the reason for that is it is not technically a final, but it is cumulative. So there will be a little bit of everything with a focus on these last 4 chapters. All right, with that, are there any questions? Oh, and I'll try to catch up with grading. I don't have much else going on today, so hopefully I'll be able to get at least caught up through last week. Would be cool. I think I even have stuff from the week before. Okay, all right. Thanks for coming. Thanks for showing up. I will see you guys again tomorrow.
Thank you.